There's something hauntingly beautiful about looking up at the night sky and realizing just how much we don't know. Beyond the familiar stars of our own galaxy, hidden in the vast cosmic ocean, lies a place where the rules of physics seem to bend, where light dances in ways we can't explain, and where mysteries pile upon mysteries, the Large Magellanic Cloud. This celestial neighbor, a satellite galaxy swirling around the Milky Way, isn't just a speck of light in the telescope. It's a treasure chest of cosmic oddities, a laboratory for the universe's strangest experiments, and tonight we're diving deep into its secrets. Imagine a place where stars vanish without a trace, where ghostly structures flicker in and out of existence, and where entire clusters of matter behave as if they're being pulled by invisible hands. The Large Magellanic Cloud isn't just another stop in the cosmos, it's a frontier of the unknown, a place where astronomers regularly stumble upon phenomena so bizarre they rewrite textbooks. And yet, despite being one of the most studied regions of space, it refuses to give up its secrets easily. What makes this galaxy so different? Why does it seem to defy our understanding at every turn? That's exactly what we're here to uncover. In this journey, we'll explore 30 of the most baffling, awe-inspiring, and downright strange phenomena hidden within the Large Magellanic Cloud. From supernova remnants that glow with unnatural energy to mysterious voids where nothing should exist. Each one of these cosmic puzzles is a piece of a grander mystery, a clue that could help us unravel the deeper workings of the universe itself. So buckle up, because we're about to venture into one of the most enigmatic corners of space, where every discovery raises more questions than answers, and that's what makes it so thrilling. The Tarantula Nebula isn't just another cloud of gas and dust, it's a cosmic powerhouse, a stellar factory operating at full throttle, churning out stars at a rate that leaves astronomers baffled. Officially known as 30 Doradus, this colossal nebula in the Large Magellanic Cloud shines with a brilliance that outshines anything else in our galactic neighborhood. If you placed it as close to us as the Orion Nebula, it would cast shadows on Earth. But here's the mystery: its luminosity doesn't just break records, it breaks the rules. Most star-forming regions glow because of young, massive stars heating the surrounding gas. But the Tarantula Nebula's brightness is off the charts, far beyond what even its dense clusters of supergiant stars should produce. Inside its swirling depths, stars like R136A1, the most massive star ever discovered, blaze with the energy of nearly 9 million suns. Yet even these behemoths can't fully explain the nebula's radiance. So what's really going on? One theory points to the unseen hand of dark matter. The Large Magellanic Cloud is already an oddball, with a lopsided distribution of this mysterious substance. Some researchers speculate that concentrated dark matter near the Tarantula Nebula could be amplifying its star formation, acting like an invisible scaffold that pulls gas together faster and more violently than normal. Others suggest the nebula might be the aftermath of a rare galactic collision, where shockwaves compressed gas into a frenzy of stellar birth. Then there's the sheer scale of the place. The Tarantula Nebula stretches over 1,000 light-years, a chaotic playground where stars don't just form, they explode. Supernovas here ripple through the gas clouds, triggering new waves of star formation in an endless cycle. It's a self-sustaining cosmic engine, one that challenges our understanding of how such regions evolve. But perhaps the most intriguing question isn't just how the Tarantula Nebula got so bright, it's what happens next. With so many massive stars packed so tightly, the nebula is a ticking time bomb. Eventually, these stars will die in spectacular supernovas, seeding the surrounding space with heavy elements and possibly even birthing black holes. For now, though, it stands as a dazzling enigma, a reminder that even in our own cosmic backyard, the universe still has secrets to spill. Deep within the tangled web of gas and dust that makes up the Large Magellanic Cloud, there's a cosmic hollow so vast and eerie it defies simple explanation. Meet N44's superbubble, a gaping void roughly 250 light-years across, a place where space itself seems to have been scooped out by some unseen hand. From a distance, this enormous cavity looks almost artificial, as if something or someone carved a perfect sphere into the nebula's heart, but the truth is far stranger. This isn't just an empty pocket in space. The walls of the superbubble glow with furious energy, lit up by the intense radiation of young, massive stars that cling to its edges like spectators at the rim of a colossal arena. Yet when astronomers peer into the center of this structure, they're met with silence. No stars, no visible remnants, just an echoing emptiness that raises one glaring question: what could possibly have created such a perfectly defined void? The leading theory suggests a series of violent supernova explosions, stellar death so powerful they punched a hole straight through the surrounding gas. Over millions of years, successive blasts could have combined their force, sweeping material outward like a cosmic snowplow. But here's the catch: the math doesn't quite add up. There aren't enough supernova remnants in the area to account for the sheer size of this bubble. That's where the alternative explanation comes in: stellar winds. Imagine the most massive stars in the region, each one blasting out supersonic gusts of charged particles with the force of a never-ending hurricane. Over time, these winds could theoretically sculpt the gas around them into this enormous cavity. But again, there's a hitch. The stars we see today don't seem powerful enough to have done the job alone. So what's really going on? Some astronomers speculate that the superbubble might be the work of an ancient generation of stars, one so massive they lived fast, died young, and vanished long before our telescopes could catch them. Others wonder if dark matter or an unseen black hole could be influencing the region, tugging at the fabric of the nebula in ways we don't yet understand. Then there's the sheer scale of the mystery. If you could float inside this bubble, the nearest walls would be so distant they'd barely appear to glow. It's a haunting thought, a space so empty yet so full of unanswered questions, and that's what makes N44's superbubble more than just a curiosity. It's a cosmic crime scene, and we're still piecing together the clues. Stories of cosmic fugitives usually belong to science fiction, but in the Large Magellanic Cloud, there's a star that's living out this very drama, a celestial outlaw racing through space at speeds that defy logic. Meet the runaway star of the LMC, a hypervelocity renegade streaking through intergalactic space so fast it could cross the distance from Earth to the Moon in just 12 minutes. Clocked at over 1,500 kilometers per second, this stellar speedster isn't just breaking the galactic speed limit, it's shattering our expectations of how stars behave in dwarf galaxies. How does a star reach such mind-bending velocities? The leading theory reads like a cosmic thriller, a close encounter with a black hole. Picture this: a binary star system, two stars orbiting each other in a graceful dance, drifting too close to the invisible monster lurking at the heart of the LMC. In a flash of gravitational chaos, one star gets captured, while the other is slingshotted outward like a stone from a sling. It's called the Hill's mechanism, and it's one of the few processes in the universe capable of accelerating a star to such extreme speeds. But here's where the mystery deepens. The LMC isn't supposed to have a supermassive black hole powerful enough to pull off this kind of gravitational heist. Our own Milky Way's central black hole, Sagittarius A star, makes sense as a cosmic catapult, but the LMC's black hole, if it even exists, should be far too small to generate these velocities. That raises a spine-tingling possibility. Could there be an unseen intermediate mass black hole hiding in the LMC's outskirts, one massive enough to fling stars into the void but small enough to have evaded detection? Then there's the star itself. Unlike most hypervelocity stars we've found in the Milky Way, which are often blue stragglers or young, massive stars, This runaway is an older, cooler object, a puzzle piece that doesn't quite fit the expected mold. Its composition tells a story of a star that's traveled far from its birthplace, picking up traces of the interstellar medium like cosmic breadcrumbs. Tracking its path backward should theoretically lead us to the scene of the crime, but instead it points to a region of the LMC with no obvious black hole or dense star cluster. What makes this runaway so revolutionary isn't just its speed, it's what it reveals about the gravitational undercurrents of dwarf galaxies. The LMC was long thought to be too small, too diffuse, to harbor the kind of extreme dynamics we associate with larger galaxies. Yet here's proof that even in these seemingly quiet corners of the universe, gravitational violence can reach staggering extremes. If stars can be ejected at these speeds, it challenges our entire understanding of how matter, and even dark matter, is distributed within the LMC. Every second, this star streaks farther into the intergalactic void, carrying with it secrets about the galaxy it fled. Will it eventually escape the LMC's gravitational grasp entirely, destined to drift alone through the cosmic dark? Or will some unseen force, a hidden black hole, a rogue dark matter clump, alter its trajectory? For now, it remains a glittering question mark against the vastness of space, a reminder that even the smallest galaxies can produce the universe's most extraordinary outlaws. We've come to expect dark matter as the universe's silent architect, the invisible hand sculpting galaxies into the shapes we recognize. So when astronomers started crunching the numbers on the Large Magellanic Cloud, they were met with a staggering realization: this galaxy isn't playing by the rules. Despite its size and structure, the LMC appears to be missing a colossal amount of the dark matter we'd expect to find. It's like weighing a freight train only to discover it's as light as a bicycle. How could a galaxy this massive defy one of cosmology's most fundamental predictions? The mystery begins with the way galaxies move. In most cases, the outer regions of a galaxy rotate faster than they should based on the visible matter alone. That discrepancy is what first clued us into dark matter's existence. It's the extra gravitational glue holding everything together. But when researchers mapped the LMC's rotation, something was off. The outer edges weren't speeding up as expected. In fact, the galaxy's motion suggested it might have only 10 to 20% of the dark matter we'd predict for its size. It's as if the LMC is running on cosmic fumes, barely held together by the gravity of the stars and gas we can actually see. One explanation points to the Milky Way's gravitational pulling. Over billions of years, as the LMC has orbited our galaxy, the Milky Way's immense tidal forces could have stripped away much of its dark matter halo, like a cosmic thief in the night, stealing the scaffolding that should anchor the LMC's structure. Computer simulations show this process, called tidal stripping, can leave smaller galaxies with significantly less dark matter than they started with. But here's the catch: the numbers still don't quite match. Even after accounting for tidal forces, the LMC's dark matter deficit is more extreme than most models predict. That's where the plot thickens. Some scientists argue we might be looking at the aftermath of a galactic collision. If the LMC once had a close encounter with another dwarf galaxy, perhaps even the small Magellanic Cloud, the gravitational chaos could have flung dark matter out into intergalactic space. Others propose an even more radical idea. What if dark matter isn't distributed the way we think? Alternative theories suggest dark matter might clump differently in smaller galaxies or interact with visible matter in ways we haven't yet accounted for. Then there's the observational challenge. Measuring dark matter isn't like counting stars. We infer its presence indirectly through subtle gravitational effects. That means uncertainties creep in. Could we be misinterpreting the data? Some researchers point to the LMC's irregular shape, arguing its chaotic structure might skew our measurements. But even after refining the models, the anomaly persists. What makes this missing dark matter so intriguing isn't just the scientific headache it causes, it's the implications. If the LMC truly has far less dark matter than expected, it forces us to reconsider how dwarf galaxies form and evolve. Maybe they don't always need hefty dark matter halos to hold themselves together. Or perhaps the LMC is a rare exception, a cosmic oddball with a unique history. Either way, this enigma reminds us that the universe still has surprises up its sleeve, even in the places we thought we understood best. In the depths of the Large Magellanic Cloud, something is feeding, and it's doing so in a way that defies every expectation we have about black holes. Meet LMC X-3, a cosmic predator locked in a deadly dance with a companion star, slurping up its material in fits and starts that leave astronomers scratching their heads. Unlike the steady, predictable glow of most black hole binaries, this system erupts in violent X-ray tantrums, flickering like a malfunctioning cosmic beacon. What makes it even stranger, it's the only black hole of its kind we've found outside the Milky Way, and its bizarre behavior is rewriting what we thought we knew about how these monsters consume their meals. Picture a black hole as a cosmic vacuum cleaner. Normally, when one orbits a star, it pulls gas from its companion in a continuous, swirling stream known as an accretion disk. That disk heats up as it spirals inward, emitting a steady hum of X-rays. But LMC X-3 doesn't play by those rules. Instead of a predictable glow, its emissions spike and crash erratically, sometimes vanishing for months before roaring back to life without warning. It's as if the black hole can't decide whether it's hungry or not, and that inconsistency has scientists racing to figure out why. One leading theory points to the companion star itself, a massive hot star that's not just passively donating material but actively fighting back. Unlike the cool, compliant stars typically found in black hole binaries, this one might be blasting out powerful stellar winds, flooding the black hole's gravitational grasp with chaotic gusts of gas. Imagine trying to drink from a fire hose. Sometimes the stream reaches your mouth, sometimes it sprays wildly off target. That could explain the X-ray flickering, a messy, unpredictable feast. But there's another twist. The accretion disk around LMC X-3 seems to warp unpredictably, bending and tilting in ways that defy our models. Normally, these disks align neatly with the black hole's equator, but here they might be wobbling like a spinning top about to fall, occasionally blocking our view of the X-rays entirely. Some researchers speculate this could be due to a hidden third object, perhaps another star or even a second black hole tugging on the disk from afar, turning what should be an orderly feeding process into a cosmic food fight. And then there's the black hole's weight. Initial estimates suggested it was around 9 times the mass of our Sun, but recent observations hint it might be heftier, possibly even tipping the scales at 15 solar masses. That's unusually massive for a black hole in a binary system, raising questions about how it formed. Did it grow by gorging on extra material over time, or was it born this big from the collapse of an extraordinarily massive star? The most tantalizing possibility, though, is that LMC X-3 isn't just a black hole. It could be a missing link in our understanding of how these objects evolve. Some theorists suggest it represents a rare intermediate stage between smaller stellar mass black holes and the supermassive giants lurking at galaxy centers. If true, studying its erratic tantrums might hold clues to how black holes grow from cosmic toddlers into the monsters that shape entire galaxies. For now, LMC X-3 remains an enigma wrapped in a mystery. Its X-ray flares like cryptic messages from the abyss. Every time we think we've figured it out, it throws another curveball, reminding us that even the most extreme objects in the universe can still surprise us. And that's what makes it so thrilling. It's not just a black hole. It's a cosmic rebel breaking all the rules. Between the large and small Magellanic Clouds, stretching across tens of thousands of light years of seemingly empty space, astronomers have found something extraordinary. an almost invisible thread of gas, delicate as a spider's silk yet vast enough to bridge galaxies. This cosmic filament, detected through the faint glow of ionized hydrogen, is the first tangible proof of a hidden highway connecting the two dwarf galaxies. But it's more than just a celestial curiosity. It's a clue to one of the universe's greatest mysteries: how galaxies communicate across the void. For decades, simulations of the cosmos predicted such filaments. The universe, after all, isn't just galaxies floating in isolation. It's a web, with strands of dark matter and gas linking everything together. But actually spotting these threads has been nearly impossible. They're too faint, too diffuse. That's what makes this discovery so groundbreaking. Using ultra-sensitive instruments, astronomers caught the faint shimmer of this filament, confirming that the LMC and SMC are literally tied together by an umbilical cord of gas. So why does this matter? For starters, it explains the strange similarities between the two galaxies. Their stars share nearly identical chemical fingerprints, suggesting they've been exchanging material for billions of years. This filament could be the delivery system, a pipeline funneling gas from one galaxy to the other. Think of it like two islands connected by an underwater current, sharing nutrients that shape their ecosystems. Only here, the nutrients are the raw materials for star formation, and the ecosystem is an entire galactic neighborhood. The filament also hints at a dramatic past. The LMC and SMC are close neighbors now, but they weren't always this way. Some models suggest they might have had a close encounter millions of years ago, a near collision that stretched and ripped gas from their outskirts, leaving this thread behind. Others propose the filament is a remnant of their birth, a relic from when both galaxies formed from the same primordial cloud. Either way, it's a fossil record of their shared history, written in hydrogen. But perhaps the most tantalizing implication is what this reveals about the intergalactic medium, the thin soup of gas filling the spaces between galaxies. This filament is proof that the universe isn't just empty blackness. It's crisscrossed by these barely detectable rivers of matter, channels that might help distribute the building blocks of stars and planets across cosmic distances. If filaments like this exist elsewhere, they could be the secret arteries of the universe, quietly feeding galaxies and shaping their evolution. What's truly astonishing is how fragile this structure appears. The gas in the filament is so sparse that, if you could stand inside it, you'd never know you were in a cosmic river. Yet despite its delicacy, it's endured for eons, resisting the pull of gravity, the blast of supernovas, and the tidal forces of two galaxies. That resilience raises another question. How many more of these filaments are out there, weaving the universe together? For now, this single thread is our first glimpse into the hidden architecture of the cosmos, a whisper of connection in the vast dark. Most stars live quiet, predictable lives, fading slowly over billions of years, but deep in the Large Magellanic Cloud, there's a celestial rebel that refuses to follow the script. Meet the star system LMC-N2, a ticking time bomb that erupts in violent outbursts like clockwork, blasting itself into visibility every few decades before fading back into obscurity. This isn't just any nova, it's a recurrent nova, one of only a handful known in the universe, and the only one of its kind found outside the Milky Way. What makes it truly bizarre isn't just the regularity of its explosions, but the fact that it shouldn't be exploding at all this often. At the heart of this system lies a white dwarf, the dense, Earth-sized corpse of a dead star, locked in a deadly embrace with a bloated red giant. Like a cosmic vampire, the white dwarf siphons hydrogen from its companion, piling the stolen gas onto its searing hot surface. Normally, this stolen fuel builds up slowly over thousands of years before reaching a critical pressure, triggering a runaway thermonuclear explosion we call a nova. But LMC-N2 doesn't wait millennia between outbursts. It erupts violently every 50 years or so, as if someone pressed fast forward on its life cycle. The reason behind this unnatural speed reveals a delicate balancing act. Most white dwarfs in nova systems are picky eaters. They only nibble at their companions' outer layers, taking in just enough hydrogen to spark an explosion every few millennia. But this white dwarf is gluttonous. Its red giant companion is unusually generous, dumping vast amounts of material onto the dwarf's surface at breakneck speed. That rapid influx of fuel heats up faster, reaching critical pressure in decades instead of centuries. The result, a cosmic pressure cooker that keeps detonating on a human timescale, lighting up the LMC like a flare in the night. Yet even this explanation leaves puzzles unsolved. Recurrent nova are supposed to be rare because they require perfect conditions. A white dwarf massive enough to compress hydrogen efficiently, paired with a donor star dumping fuel at just the right rate. LMC N2's 50-year cycle is shorter than any model predicts, suggesting something else might be tweaking the equation. Some astronomers speculate the white dwarf could be rotating at extreme speeds, flinging material outward and altering how heat spreads across its surface. Others wonder if the red giant's stellar winds are unusually chaotic, creating pockets of denser gas that ignite prematurely. And then there's the bigger mystery: what happens next? Every explosion leaves the white dwarf slightly heavier, inching it toward a catastrophic tipping point. Most recurrent nova are thought to be precursors to Type Ia supernova, the universe's ultimate fireworks, triggered when a white dwarf steals so much mass it collapses under its own weight. But LMC N2's rapid cycle means it's accumulating mass faster than expected. Could it be racing toward its demise, or is there some unseen mechanism, a stellar diet plan, if you will, preventing it from reaching the brink? For now, this enigmatic system keeps erupting on schedule, a cosmic metronome ticking toward an uncertain future. Each outburst sprays heavy elements like carbon and oxygen into space, seeding the LMC with the building blocks of planets and life. And with every explosion, astronomers get another chance to decode its secrets, peeling back the layers of one of the most extreme stellar relationships in the universe. It's a reminder that even the most violent processes in space can follow a rhythm if you're patient enough to listen. In the crowded stellar neighborhoods of the Large Magellanic Cloud, where stars typically form in bustling clusters like cosmic cities, astronomers have stumbled upon something that shouldn't exist: loners. Not just any loners, but dazzling blue stars blazing with youthful energy, scattered across empty reaches of space like forgotten embers from a celestial fireworks show. These aren't the aging, reddened stars we'd expect to find in isolation. They're blue dwarfs, stellar adolescents burning so hot they should only exist in the nurseries of dense gas clouds. Yet here they are, shining alone in the void, defying everything we thought we knew about how stars are born. The mystery begins with their color. Blue stars are the universe's overachievers, massive, searingly hot, and short-lived. They burn through their fuel so quickly they rarely last more than a few 100 million years, a blink in cosmic time. Normally, such stars form in packed stellar nurseries where collapsing gas clouds fragment into dozens or hundreds of siblings. But these blue dwarfs have no siblings, no surrounding gas, no trace of the crowded environments we associate with their formation. It's as if someone plucked them from their birthplaces and scattered them across the galaxy like seeds in the wind. So how did they get there? One theory suggests they might be runaway stars, ejected from clusters by violent gravitational interactions. Picture a game of cosmic pinball. When massive stars swing too close to each other, their gravitational kicks can fling one outward at astonishing speeds. Over time, these outcasts could drift far from their birthplace, leaving no visible trail back home. But there's a problem. The velocities required to explain some of these isolated blue stars are extreme, beyond what typical cluster dynamics should produce. Another possibility is that they formed right where we see them, in pockets of gas too sparse to create full-fledged clusters. Recent simulations show that under just the right conditions, subtle density fluctuations in the interstellar medium, or shock waves from distant supernovas small, isolated clouds might collapse into single stars rather than clusters. If true, it would mean star formation is far more flexible than we realized, capable of stitching solitary stars into the galactic tapestry wherever the cosmic fabric wrinkles just so. Then there's the strangest twist. Some of these blue loners appear to be aging in reverse. Spectroscopic studies reveal a handful with atmospheric compositions that suggest they're actually older stars recently rejuvenated, either by cannibalizing a smaller companion or by colliding with another star in a rare cosmic merger. Imagine a middle-aged star suddenly injecting itself with stellar botox, its outer layers stripped away to expose the hotter, younger-looking core beneath. It's a stellar makeover so drastic it fools our telescopes into seeing a newborn where an elder actually stands. The implications ripple far beyond the LMC. If stars can form or fake their youth in isolation, it challenges our fundamental models of galactic evolution. Could the early universe have been seeded with such lone blue pioneers, their intense radiation shaping the chemistry of entire galaxies? Might we need to rethink how we measure stellar populations in distant galaxies, where what looks like a thriving nursery could actually be a graveyard of imposters? For now, these blue dwarfs remain cosmic outliers, their very existence a reminder that the universe has more than one way to light up the dark. Galaxies are supposed to be elegant whirlpools of stars spinning with serene symmetry, but the Large Magellanic Cloud has clearly missed that memo. Gaze at any image of this dwarf galaxy, and the first thing you'll notice is its chaotic, lopsided silhouette, as if some cosmic toddler took a bite out of its edges. This isn't just a case of bad celestial posture. The LMC's entire structure is buckling under forces so intense they're stretching the galaxy like taffy. And the culprits, a gravitational tug of war with two of its closest neighbors, the Milky Way and the Small Magellanic Cloud. The evidence of this cosmic wrestling match is written across the galaxy's twisted form. Normally, a galaxy's disk should be flat and orderly, with stars orbiting in neat, concentric circles. But the LMC's disk is warped, its outer regions bent upward on one side and downward on the other, like a vinyl record left too long in the sun. Even stranger, one entire section of the galaxy seems to be lagging behind, trailing off into space like a comet's tail. Astronomers call this the off-plane population, a swarm of stars drifting out of sync with the rest of the galaxy's rotation. So what's bending the LMC out of shape? The prime suspect is the Milky Way's overwhelming gravity. As the LMC orbits our galaxy, it's caught in a relentless tidal pull, the same force that gives Earth its ocean tides just on a galactic scale. The side of the LMC closest to the Milky Way feels a stronger tug than the far side, stretching the dwarf galaxy like a piece of elastic. Over billions of years, this has twisted the LMC's disk into its current crumpled state. But the Milky Way isn't acting alone. The Small Magellanic Cloud, the LMC's smaller sibling, has been stirring the pot too. Computer simulations suggest these two dwarf galaxies had a close encounter, possibly even a collision within the last few billion years. That near miss would have sent shockwaves through the LMC's gas and stars, further distorting its shape. Some researchers argue it might even explain the galaxy's bizarre bar, a bright central ridge of stars that seems misaligned with the rest of the disk. The real puzzle, though, is how the LMC hasn't been torn apart completely. Despite the relentless pulling and twisting, the galaxy is still forming stars, still clinging to its identity. Some scientists think dark matter might be the invisible skeleton holding it together, providing just enough extra gravity to resist total disintegration. Others point to the LMC's unusual gas distribution, which could be acting like a shock absorber, cushioning the galaxy from the worst of the tidal forces. But here's the twist: the LMC's days as a distorted oddball might be numbered. Recent measurements suggest it's on its first pass around the Milky Way, meaning these gravitational interactions are relatively new in cosmic terms. As it continues its orbit, the tides will grow stronger, the warping more extreme. One day, the LMC may look nothing like it does now, its stars slowly stripped away, its structure unraveled into a stream of cosmic debris. For now, though, it stands as a living lesson in galactic survival, proving that even in the brutal gravitational arena of the universe, beauty can thrive in chaos. In the grand tapestry of the Large Magellanic Cloud, where stars of every size and color blaze against the cosmic dark, there's a glaring absence, a void where science insists there should be giants. Red supergiants, those swollen, aging behemoths that mark the final fiery chapters of massive stars' lives, are vanishingly rare in the LMC. And that's not just a curious observation, it's a full-blown crisis for astrophysics, one that threatens to upend our understanding of how the most massive stars live and die. The numbers tell the story. Based on what we know about stellar populations, the LMC should be teeming with hundreds of these crimson titans. These are stars 10 to 20 times heavier than our Sun, stars so vast they could swallow Jupiter's orbit whole. They're supposed to dominate the late stages of stellar evolution, their outer layers puffing up like cosmic balloons as they burn through their nuclear fuel. Yet when astronomers count them, the LMC comes up shockingly short. Some estimates suggest we're seeing only a third of the red supergiants our models predict. It's as if the universe skipped a chapter in the stellar life cycle manual, leaving scientists scrambling to explain why. One leading theory points to the LMC's unique chemistry. Unlike the Milky Way, this galaxy is metal-poor not in the sense of iron and gold, but in astronomical terms, where metals mean any element heavier than hydrogen and helium. That deficiency might be altering how these massive stars evolve. In metal-rich environments, a star's outer layers become opaque as heavier elements absorb radiation, causing the star to swell into a red supergiant. But in the LMC's low-metal cocktail, stellar atmospheres could remain more transparent, allowing radiation to escape more efficiently. The result, stars that stay hotter and more compact, skipping the red supergiant phase entirely or passing through it so quickly we rarely catch them in the act. Then there's the explosive alternative. Maybe these stars aren't missing. They're just meeting violent ends before we can spot them. Some researchers suggest the LMC's red supergiants might be collapsing directly into black holes without the fanfare of a supernova, a phenomenon called failed supernova. Normally, when a massive star exhausts its fuel, its core collapses in a spectacular explosion visible across the universe. But under certain conditions, the core might implode silently, the star winking out of existence like a candle snuffed in the wind. If this is happening in the LMC, it would explain both the scarcity of red supergiants and the surprising number of black holes we've detected there. But the plot thickens when we look at the red supergiants we do find. Many of them are behaving strangely, their surfaces bubbling with turbulent convection unlike anything seen in our galaxy. Some exhibit bizarre chemical signatures, their atmospheres peppered with excess carbon or nitrogen traces of internal material dredged up by intense mixing. These anomalies hint that the LMC's red supergiants aren't just fewer in number, they're fundamentally different beasts evolving under rules we're only beginning to decipher. What makes this mystery so consequential isn't just the missing stars, it's what they represent. Red supergiants are cosmic alchemists, forging the heavy elements that seed future generations of stars and planets. If they're vanishing prematurely or evolving differently, it could reshape the entire chemical trajectory of the LMC. Even more crucially, these stars are the progenitors of the most energetic explosions in the universe type Roman II supernova. Misjudge their numbers, and our calculations for everything from galactic evolution to the rate of star birth across cosmic time could be wildly off. For now, the red supergiant problem remains one of the LMC's most stubborn puzzles, a reminder that even the most well-trodden paths of stellar physics can lead to uncharted territory. Every telescope pointed at this galaxy brings us closer to an answer, or perhaps to an even deeper question. Globular clusters are supposed to be among the most dazzling sights in the cosmos, dense spheres of hundreds of thousands of stars glittering like celestial chandeliers. But in the Large Magellanic Cloud, astronomers have stumbled upon something that defies this glittering stereotype. Clusters so dark they barely emit a whisper of light. These shadowy gatherings, known as dark globular clusters, aren't just dim. They're missing almost all the starlight their size and mass suggest they should produce. It's as if someone took a normal cluster and swapped out 90% of its stars with invisible phantoms. So what's hiding in these cosmic blind spots? The leading explanations sound like something from a sci-fi thriller, swarms of black holes, or perhaps something even more elusive, clumps of pure dark matter. The mystery starts with their weight. When researchers measured the gravitational pull of these clusters, they found them far heavier than their faint glow could account for. A typical globular cluster's mass aligns neatly with the number of stars it contains, but these dark anomalies weigh 10 times more than their visible stars should allow. That discrepancy screams missing mass, and in the universe, when something has gravity without light, the usual suspects are black holes or dark matter. Black holes make for a compelling villain in this cosmic whodunit. Imagine a cluster where stars have been colliding and merging for billions of years, their remnants collapsing into stellar mass black holes. Over time, these black holes could sink to the cluster's core, drawn together by their immense gravity, leaving the few surviving stars orbiting like distant satellites. Simulations suggest such a scenario could create a nearly invisible structure, its heart packed with dozens, maybe hundreds, of these dark predators. There's precedent for this. In our own Milky Way, astronomers have found clusters with surprising numbers of black holes. But the LMC's dark clusters take it to extremes, pushing the idea to its limits. Then there's the dark matter angle. Normally, globular clusters are thought to be clean of dark matter, their stars orbiting under their own collective gravity. But what if these dark clusters are different? Could they be primordial relics formed in the early universe when dark matter was more densely concentrated? Some theorists propose these structures might be the stripped cores of ancient dwarf galaxies, their outer stars torn away by tidal forces, leaving behind a dark matter-rich husk. It's a radical idea, one that would force us to rewrite how we think globular clusters are born. What makes this puzzle even thornier is the light we do see. The few visible stars in these clusters aren't behaving normally. Their orbits are faster and more erratic than expected, as if they're being yanked around by unseen forces. Some show bizarre chemical compositions, hinting they've been bathed in radiation from violent, unseen events, perhaps collisions between those hidden black holes. And then there's the eerie absence of pulsars. In most globular clusters, these rapidly spinning neutron stars are common, their radio beacons lighting up telescopes. But in the dark cluster's silence, it's as if something has swept them away or prevented them from forming in the first place. The stakes here are higher than just solving a cosmic curiosity. If these clusters are black hole hubs, they could be the factories where gravitational waves are forged, their hidden collisions rippling space-time. If they're dark matter labs, they might hold clues to one of the universe's deepest mysteries. Either way, they're forcing us to confront an uncomfortable truth. The universe is still full of shadows, and some of them might be hiding in plain sight. If galaxies had traffic laws, the Large Magellanic Cloud would be getting pulled over for reckless driving. Tucked away in its swirling disk of gas and stars is a rogue cloud moving against the flow, a cosmic speedster going the wrong way down a one-way street. This isn't just a minor oddity, it's an entire gas structure thousands of light years across, rotating in the opposite direction to the rest of the galaxy. Picture a whirlpool where suddenly, against all logic, a massive current starts spinning backward. That's the level of chaos we're dealing with here, and it points to a violent history written in hydrogen. The discovery came when astronomers mapped the motion of the LMC's gas using radio telescopes. Most of the galaxy's material orbits in a predictable clockwise dance, but one colossal cloud, dubbed the Rebel, was caught red-handed moving counter-clockwise at nearly 100 kilometers per second. Gas clouds don't just decide to rebel, they're slaves to gravity, following the path set by the galaxy's rotation. So how did this one break free? The leading theory reads like an intergalactic crime scene reconstruction. Billions of years ago, the LMC may have collided with another dwarf galaxy, perhaps even its sibling, the Small Magellanic Cloud. In the gravitational chaos of that encounter, a chunk of gas could have been ripped away, flung into an orbit so extreme it reversed direction. Think of it like a carousel where someone hurls a bucket of water against the spin. Some of that water might cling to the ride but move backward, defying the flow. Over time, as the LMC's gravity reasserted control, this rogue gas would have settled into its current, counter-rotating path. But there's a twist. The Rebel isn't just moving backward, it's younger than most of the galaxy's gas. Chemical analyses reveal it's richer in heavy elements like oxygen and carbon, the kind forged in stars and scattered by supernovas. That means it couldn't have been lingering since the galaxy's birth. It must have been contaminated by stellar explosions after it went rogue. This has led some researchers to propose an even wilder origin story. Maybe the Rebel isn't stolen gas at all, but the corpse of a devoured star cluster. When dense clusters orbit a galaxy, their stars can be stripped away by tidal forces, leaving behind trails of gas that inherit the cluster's original opposing motion. Then there's the dark matter factor. The LMC's dark matter halo, what's left of it, isn't perfectly spherical. Its lopsided distribution could create gravitational eddies capable of flipping gas clouds into backward orbits. If true, the Rebel might be a visible tracer of invisible forces, a flickering signpost pointing to the galaxy's unseen scaffolding. What makes this counter-rotating gas so much more than a curiosity is its role in the LMC's future. Gas clouds like these are star factories, and stars born from backward-moving material inherit that rebellious motion. Over time, they'll carve chaotic paths through the galaxy, muddying its orderly rotation. Some might even be flung free entirely, joining the ranks of hypervelocity stars escaping into intergalactic space. For now, the Rebel spins on, a fossil of ancient violence and a reminder that even in the vastness of space, no act of cosmic vandalism goes unnoticed. Every backward loop is a clue, one that might help us piece together not just the LMC's history, but the untold stories of galaxies across the universe. Some corners of the universe seem to have a taste for destruction, and in the Large Magellanic Cloud, there's one region that's practically addicted. A stretch of space so prolific in stellar explosions, it's earned the nickname the Supernova Factory. Nestled within the galaxy's chaotic spiral arms, this area has produced more supernovas than anywhere else in the local universe, including the most famous stellar detonation of modern times, SN 1987A. But why here? What makes this patch of sky the universe's favorite demolition zone? The secret lies in its stellar population. This region is stacked with massive, short-lived stars, cosmic powder kegs burning through their fuel at breakneck speed. While stars like our Sun might live for billions of years, these behemoths rage through their entire life cycles in just a few million. Their immense gravity cranks up internal pressures, forcing nuclear fusion to run at unsustainable rates. It's the cosmic equivalent of revving an engine until it explodes. Yet even among clusters of massive stars, this area stands out. The Supernova Factory stars aren't just big, they're jammed together with extraordinary density, packed so tightly that their solar winds constantly collide, creating turbulent shockwaves that ripple through the surrounding gas. This environment appears to accelerate stellar evolution, as if the stars themselves are being pushed toward their explosive fates by some unseen celestial peer pressure. Then there's the chemical fingerprint. The gas here is laced with an unusual cocktail of heavier elements, debris from countless past supernovas that seeded the clouds with the raw materials for new stars. Each generation of stars that forms here inherits this enriched fuel, which alters how they burn and ultimately how they die. It's a self-perpetuating cycle. More explosions create more heavy elements, which lead to more unstable stars, priming the region for future detonations. SN 1987 offers the perfect case study. That explosion wasn't just bright, it was bizarre. Unlike most supernovas that fade predictably, this one brightened in unexpected waves, as if something inside the wreckage kept reigniting. Years later, we discovered why. The star hadn't died a clean death. Before exploding, it had likely been part of a binary system, its outer layers siphoned away by a companion star, leaving behind a misshapen core that detonated in an asymmetrical fireball. This kind of complex stellar relationship seems common in the supernova factory, where gravitational tangles between stars may be cranking up the frequency and strangeness of explosions. But the most tantalizing clue might be hiding in the aftermath. When astronomers point radio telescopes at this region, they pick up faint echoes of past supernovas, ghostly rings of gas expanding outward from ancient blasts we never witnessed. These relics suggest the factory's demolition spree isn't a recent phenomenon. It's been operating for millions of years, possibly since the LMC first formed. What does this mean for the future? With so many massive stars still waiting their turn, the supernova factory shows no signs of closing shop. Each explosion reshapes the landscape, carving bubbles in the interstellar medium that trigger new star formation even as they snuff out old stars. It's a breathtaking reminder that in the cosmos, destruction and creation are two sides of the same coin. And in this corner of the LMC, that coin keeps flipping at a dizzying pace. The Large Magellanic Cloud wears its scars like cosmic tattoos, and none are more haunting than the twin specters glowing faintly in gamma rays, towering above its disk like ghostly hourglasses. These aren't your typical stellar remnants or supernova debris. They're colossal bubbles, each stretching tens of thousands of light years into space, their surfaces shimmering with high-energy radiation. What makes them so eerie isn't just their size or their ghostly glow, it's the fact that no one knows for sure what cosmic event left them behind. Gamma-ray bubbles are the universe's version of a smoke signal, evidence of some cataclysm so powerful it blasted energy far beyond a galaxy's usual boundaries. In the Milky Way, we've seen similar structures, Fermi bubbles, likely carved by our supermassive black hole's outbursts millions of years ago. But the LMC doesn't have a central black hole hefty enough to create such havoc. So one clue lies in the bubble's chemistry. Their gamma-ray signature suggests a cascade of fast-moving particles slamming into slower gas, like cosmic fireworks ignited by a shockwave. That's led some astronomers to point to the LMC's wild youth, when bursts of star formation may have flooded the galaxy with supernovas. Picture this, a golden age, millions of years ago, when stars were born and died in such rapid succession that their collective explosions blew a pair of titanic bubbles into intergalactic space. The energy would have funneled outward along the galaxy's poles, sculpting these faint, lingering monuments. But there's a competing theory, one that's even more dramatic. What if the LMC once had an active galactic nucleus, a supermassive black hole that's since gone quiet? While the galaxy lacks a heavyweight black hole today, it's possible one lurked in its core long ago, flaring up just long enough to inflate these bubbles before running out of fuel and fading into obscurity. It's a tantalizing idea because it would mean the LMC's quiet present belies a violent past, one where it briefly mimicked the behavior of galaxies 10 times its size. Then there's the dark matter angle. Some researchers speculate these bubbles could be the aftermath of dark matter particles annihilating each other in the galaxy's halo, releasing gamma rays as they collide. It's a long shot, but if true, these faint structures could be our first glimpse of dark matter's hidden interactions on a galactic scale. What's undeniable is their longevity. Unlike supernova remnants, which fade within millennia, these bubbles have persisted for millions of years, their energy dissipating so slowly they've become near-permanent fixtures. They're like echoes of a shout across cosmic time, a reminder that even in a galaxy as small as the LMC, the past can leave marks too big to ignore. And as gamma-ray telescopes grow more sensitive, these ghostly structures may finally reveal their secrets, whether they're tombstones for a lost black hole, relics of a stellar baby boom, or something even stranger. Galaxies aren't just born sometimes, they're ripped from the wreckage of cosmic collisions like sparks from a grinding wheel. Scattered around the Large Magellanic Cloud, astronomers have spotted a flock of cosmic strays, tiny, isolated galaxies so peculiar they shouldn't exist at all. These aren't your typical dwarfs, they're tidal dwarfs, celestial orphans forged from the shredded debris of galactic smash-ups, and their very existence is forcing us to rewrite the rules of how galaxies form. What makes these objects so strange is their origin story. Traditional dwarf galaxies are ancient relics thought to have coalesced from pristine gas in the early universe. But tidal dwarfs are newcomers, stitched together from the gas and stars ripped free during violent encounters between larger galaxies. Picture two galaxies grazing each other, their gravitational forces stretching long streams of material into space like taffy pulled apart. Sometimes those streams collapse under their own gravity, clumping into new, tiny galaxies. It's cosmic recycling on a grand scale, turning galactic wreckage into something entirely new. The LMC's tidal dwarfs are particularly baffling because they're survivors. These fragile structures shouldn't last long in the gravitational chaos of intergalactic space. Yet here they are, orbiting the LMC like ducklings trailing their mother, their delicate structures intact despite the tides and pulls of nearby galaxies. Take, for example, one of the most studied tidal dwarfs near the LMC, a wispy, gas-rich speck called Object Name. Spectroscopic studies reveal it's brimming with young stars, a telltale sign it formed recently from fresh material rather than primordial gas. Even more telling, its chemical makeup matches the LMC's outer regions almost perfectly, as if it were literally carved from the larger galaxy's flesh. But the real shocker, these tidal dwarfs might be hiding a dark secret, or rather, lacking one. Unlike classic dwarfs, which are thought to be anchored by hefty dark matter halos, tidal dwarfs appear to be running on gravity alone. When astronomers measure their rotation speeds, they don't see the extra pull that dark matter should provide. Instead, these galaxies seem to be held together purely by the visible stars and gas they contain, making them cosmic rule breakers in a universe where dark matter is supposed to reign supreme. That absence raises a radical question. Could some of the classic dwarf galaxies we've catalogued actually be tidal imposters? If tidal dwarfs can mimic their ancient counterparts, it might mean our galactic family tree is due for a serious pruning. It's a twist that could reshape our understanding of galactic evolution, blurring the line between true primordial dwarfs and these recycled upstarts. Then there's the LMC's own role in this drama. The presence of tidal dwarfs suggests the galaxy has been through more violent encounters than we thought, not just with the small Magellanic Cloud, but perhaps with other, now vanished companions. Each dwarf is a fossil of past chaos, a clue to collisions that might have shaped the LMC's lopsided structure and missing dark matter. For now, these tiny galaxies remain understudied curiosities, often overshadowed by their larger neighbors. But their very existence is a reminder that the universe has more than one way to build a galaxy, and sometimes the most unassuming objects can upend our deepest assumptions. Stars are supposed to follow a recipe, a predictable blend of elements forged in their cores and dredged up to their surfaces as they age. But in the Large Magellanic Cloud, astronomers have discovered a celestial kitchen rebellion. Carbon stars here aren't just common, they're overflowing. Their atmospheres so saturated with carbon that they defy everything we thought we knew about how stars evolve, especially in a metal-poor galaxy like this one. These aren't just curiosities, they're cosmic contradictions, and they're forcing us to rethink the very chemistry of the universe. Take a carbon star in the Milky Way, and you'll find a dying giant, a red giant in its twilight years, having burned through its helium and now puffing carbon-rich soot into space like a cosmic steampunk engine. These stars are rare in our galaxy because they require very specific conditions. Just enough heavy elements to form carbon, but not so many that oxygen dominates and binds it all up in carbon monoxide. The LMC, with its lower metal content, should have even fewer of these carbon-rich oddballs. Yet somehow, it's teeming with them, their spectral signatures popping up like a chemical rebellion against the rules. The mystery isn't just their abundance, it's their location. Many of these carbon stars are younger than expected, nestled in regions where stars shouldn't have had time to evolve to the carbon-producing phase. It's like finding a forest full of ancient trees in a place that was barren desert just a century ago. Some are even part of binary systems, their companion stars influencing their chemistry in ways we can't yet explain. One theory points to the LMC's unique star-forming history. Unlike the Milky Way, which has been churning out stars at a steady pace for billions of years, the LMC has experienced violent bursts of star formation periods where thousands of massive stars were born and died in rapid succession. Those deaths would have seeded the galaxy with carbon much faster than normal, flooding the interstellar medium with raw material for future stars. When the next generation formed, they might have started life already carbon-rich, skipping steps in the usual stellar aging process. Then there's the role of convection, the churning motion that brings elements from a star's core to its surface. In metal-poor stars like those in the LMC, convection zones might penetrate deeper, dredging up carbon earlier and more efficiently than in their Milky Way counterparts. It's as if these stars have hyperactive internal elevators, shuttling carbon upwards before oxygen can lock it away. But the real curveball comes from the stars themselves. Some of the LMC's carbon stars show traces of lithium, an element that's usually destroyed in stellar interiors. Its presence suggests these stars are somehow creating fresh lithium as they age, a process so rare it's like finding a car that manufactures its own gasoline. No current model of stellar nucleosynthesis explains this, leaving theorists scrambling to rewrite the textbooks. What makes this cosmic chemistry experiment so tantalizing is its implications. Carbon is the backbone of life, the element that connects stars to planets to biology. If the LMC's carbon stars are overproducing it, they might be seeding their surroundings with building blocks for future worlds at an unprecedented rate. And if that's happening here, it could mean pockets of the early universe, equally metal-poor, were far more fertile for organic chemistry than we ever imagined. For now, these carbon-rich rebels stand as a reminder that the universe doesn't follow neat, universal rules. Sometimes it tosses the recipe book out the window, and the results are more fascinating than we could have dreamed. Among the countless treasures peppered across the Large Magellanic Cloud, one anomaly stands out not for its brightness or size, but for its sheer violence, an overabundance of X-ray binaries, celestial duos so volatile they shine with the fury of a million suns. While most galaxies host a handful of these high-energy systems, the LMC is practically overflowing with them, packing nearly twice as many as astronomers would predict for its size. It's as if some unseen cosmic hand cranked up the dial on stellar violence here, leaving scientists scrambling to figure out why this dwarf galaxy became the universe's preferred stage for these explosive performances. At the heart of each X-ray binary lies a partnership forged in chaos, a normal star locked in orbit with either a neutron star or a black hole, its outer layers slowly being devoured by its ravenous companion. As this stolen gas spirals toward the compact object, it heats up to millions of degrees, unleashing torrents of X-rays visible across intergalactic space. What makes the LMC's abundance so puzzling isn't just the number of these systems, it's their bizarre distribution. Unlike the Milky Way, where X-ray binaries tend to cluster near the crowded galactic center, the LMCs are scattered haphazardly, some even lurking in its sparse outer reaches. The leading suspect behind this overdensity is the LMC's tumultuous star-forming history. This galaxy hasn't built stars at a steady pace, it's experienced violent bursts of creation, epochs where vast stellar nurseries birthed generations of massive stars in rapid succession. These stars live fast, die young, and often leave behind neutron stars or black holes with plenty of nearby companions to feast on. Simulations suggest these starburst periods would have produced a bumper crop of massive binaries, the perfect precursors to today's X-ray binaries. Over time, as the more massive star in each pair collapsed, its remnant could have easily gravitationally enslaved its sibling, creating the explosive duos we see today. But there's another twist: the LMC's low metallicity, its scarcity of elements heavier than hydrogen and helium, might be supercharging the process. In metal-poor environments, massive stars tend to lose less mass through stellar winds, meaning they hold onto more of their bulk right up until death. This could lead to more massive stellar remnants, particularly black holes, which would then have stronger gravitational pulls to siphon gas from their companions. It's a cosmic feedback loop. Fewer metals mean heavier black holes, which mean brighter X-ray binaries, which in turn enrich the galaxy with heavier elements through their explosions. Then there's the wild card: dynamical formation. The LMC's chaotic gravity dance with the Milky Way and small Magellanic Cloud could have shaken loose countless stars from their original orbits, increasing the chances of close encounters that forge new X-ray binaries. Picture a crowded dance floor where galaxies swinging past each other send stars careening into new partnerships, some of which turn violently one-sided. What makes these X-ray binaries more than just cosmic curiosities is their role as galactic power plants. Their intense radiation carves bubbles in the interstellar medium, influencing where and how new stars form. Their explosions seed the galaxy with heavy elements, forging the ingredients for future planets and perhaps life. And for astronomers, they're natural laboratories, offering front-row seats to the extreme physics of gravity and particle acceleration that we could never replicate on Earth. The LMC's excess might be a quirk of its unique history, or it might hint at deeper universal truths about how galaxies evolve when left to simmer in isolation. Either way, these blazing binaries are more than just overachievers. They're windows into the forces that shape galaxies, one stellar cataclysm at a time. Globular clusters are the universe's most loyal citizens, tightly bound families of stars that orbit their host galaxies with quiet dignity, sticking together for billions of years. But in the Large Magellanic Cloud, some of these ancient stellar communities have gone rogue, hurtling through space at speeds so extreme, they're practically fleeing the scene of a cosmic crime. These aren't just fast-moving clusters, they're runaways ejected from their birthplace with such force. They're on trajectories that might one day fling them right out of the galaxy. And the story of how they got here reads like a gravitational thriller. Most globular clusters inch along at a leisurely pace, their orbits shaped by the gentle tug of their galaxy's overall gravity. But the LMC's runaway clusters are different, some racing at hundreds of kilometers per second, faster than any known mechanism should allow, the leading explanation. A close encounter with something massive enough to slingshot them into hyperspeed. Picture a cluster drifting too near the LMC's central bar, where dense star clouds create a gravitational maelstrom. A precise alignment could see the cluster whipped around like a stone from a sling, gaining enough speed to escape its original orbit entirely. But there's a twist. Some of these renegades aren't just fast, they're backwards. Their motion opposes the rotation of the galaxy itself, as if they were hurled into reverse by some unseen force. That peculiar detail points to an even more dramatic origin story, a galactic collision. If the LMC once grazed the small Magellanic Cloud or another dwarf galaxy, the gravitational chaos could have sent clusters careening in all directions, some flung forward, some backward, like billiard balls scattered by a break shot. Simulations show such encounters can eject clusters with precisely the velocities we observe, turning them into celestial fugitives. What makes these runaways especially valuable is what they reveal about the LMC's hidden structure. By tracing their paths backward, astronomers can map the galaxy's gravitational field in ways that visible light alone can't. Some clusters' trajectories hint at unseen masses, perhaps clumps of dark matter or the ghostly remnants of long-dead star clusters tugging at them as they flee. Others seem to have been accelerated by the LMC's own motion around the Milky Way, their speeds a fossil record of the tidal forces warping the galaxy. Then there's the survival question. Globular clusters are delicate ecosystems held together by a fragile balance of gravity. Being hurled through space at these speeds should tear them apart, yet these fugitives remain intact. Their resilience suggests they're denser than we thought, their cores packed with enough stars to withstand the galactic equivalent of a hurricane. That robustness could rewrite our understanding of how globular clusters form and evolve, especially in chaotic environments like the LMC. The most tantalizing runaway of all might be one currently streaking toward the Milky Way. If it maintains its course, it could become the first intergalactic globular cluster ever captured by our galaxy, a celestial immigrant with a story etched in its stars. Studying its composition could reveal what the LMC was like when the cluster fled, offering a time capsule of the dwarf galaxy's youth. For now, these speeding clusters are more than just anomalies, they're messengers. Each one carries clues about the violence that shaped the LMC, the invisible forces weaving through it, and the dynamic processes that continue to sculpt galaxies even today. They prove that in the cosmos, even the oldest, most seemingly stable structures can be set adrift, and sometimes it's the runaways that show us the way home. The Large Magellanic Cloud has a stellar retirement problem, and it's baffling astronomers. When sun-like stars reach the end of their lives, they're supposed to bow out in a blaze of glory, shedding their outer layers in glowing halos we call planetary nebulae. These cosmic farewell performances are meant to be common, predictable fixtures in galaxies. But in the LMC, they're vanishingly rare. Despite housing billions of stars at just the right age and size to produce these shimmering death shrouds, the galaxy appears to be missing up to 80% of its expected planetary nebulae. It's as if entire generations of stars are slipping away into the night without saying goodbye, and the implications could rewrite what we know about stellar afterlife. The mystery starts with the numbers. Based on the LMC's star formation history and the known rates of planetary nebula formation in similar galaxies, astronomers expected to find thousands of these glowing shells. Instead, surveys have uncovered only a few hundred. Even accounting for observational challenges, planetary nebulae are faint and easy to overlook. The deficit is staggering. Something about the LMC's environment appears to be short-circuiting the standard stellar death sequence, leaving stars to fade quietly rather than lighting up the cosmos one last time. One clue might lie in the galaxy's chemical makeup. Unlike the Milky Way, the LMC is metal-poor, meaning it contains fewer heavy elements fused in previous stellar generations. These elements play a crucial role in how stars eject their outer layers late in life. Normally, dust grains, tiny particles rich in carbon and silicon, form in a dying star's atmosphere, absorbing light and pushing the gas outward through radiation pressure. But in the LMC's low metal environment, there may not be enough dust to drive this process efficiently. Without that critical push, the star's outer layers might collapse back inward or dissipate too slowly to form the bright, compact nebulae we recognize. Then there's the stellar weight factor. The mass of a star at death determines whether it becomes a planetary nebula at all. In the Milky Way, stars between 1 and 8 times the Sun's mass reliably produce these glowing shrouds. But in the LMC, where stars form with slightly different mass distributions due to the lower metal content, many might skip the planetary nebula phase entirely, either collapsing directly into white dwarfs or shedding their material so gradually it never lights up. The most tantalizing possibility, though, involves the LMC's turbulent history. Planetary nebulae are delicate structures, lasting only tens of thousands of years before fading into the interstellar medium. If the galaxy experienced bursts of star formation followed by long quiet periods, as evidence suggests many nebulae from earlier epochs might have already dissolved, their atoms recycled into new stars before our telescopes could catch them. It's like arriving at a fireworks show just as the last embers fade. The absence doesn't mean the explosions never happened, only that we missed the spectacle. What makes this deficit more than just a cosmic accounting error is its ripple effect. Planetary nebulae are the universe's primary distributors of carbon, nitrogen, and other life-essential elements. If they're rarer than we thought in galaxies like the LMC, it could mean these building blocks are scattered more thinly, altering the chemistry of future stars and planets. It might even change how we interpret similar metal-poor galaxies in the distant universe, where planetary nebulae are too faint to detect directly. For now, astronomers are racing to solve the case of the missing nebulae, combing through infrared and radio data for traces of their faint, cold remnants. Every ghostly shell they find is a clue, not just to how stars die in this peculiar galaxy, but to how the cosmos recycles itself, one silent departure at a time. Galaxies aren't just stars, they're ecosystems, with bustling cores fading out to sparse halos where only the hardiest stars wander. But the Large Magellanic Cloud has a halo unlike any other, a ghostly outskirt so underpopulated, it's like finding a city where the suburbs never got built. While most galaxies scatter ancient stars generously across their outer reaches, the LMC's halo is a cosmic desert. Its stars spread so thin they barely register against the blackness of space. This missing stellar fringe isn't just a curiosity, it's a glaring clue that this galaxy's past was far more turbulent than its calm present suggests. The first hints of this anomaly came from painstaking surveys mapping the LMC's faint outer glow. Astronomers expected to find the usual sprinkling of aging red giants and ancient stellar relics orbiting far from the main disk, the galactic equivalent of finding seashells left by receding tides. Instead, they uncovered vast tracts of near-nothingness with stellar densities up to 10 times lower than comparable galaxies. It'd be like expecting a forest and finding only occasional, gnarled trees standing alone in a wasteland. One explanation digs into the LMC's violent backstory. Halos typically grow in two ways, through the slow accumulation of gas over billions of years or through galactic cannibalism, swallowing smaller dwarf galaxies whole. The LMC's star-poor halo might be evidence it missed both opportunities. Unlike the Milky Way, which has feasted on dozens of smaller companions, the LMC may have spent most of its existence in lonely isolation, never gathering enough material to build a proper stellar halo. But there's a twist that makes this even stranger. The stars it does have in its halo are behaving oddly. Some orbit at extreme angles, tilted almost perpendicular to the galaxy's disk. Others move in tight, looping paths that suggest they were captured recently, perhaps during the LMC's ongoing collision with the small Magellanic Cloud. These stellar interlopers could be the shredded remains of a dwarf galaxy the LMC tore apart. its stars now strewn chaotically through the halo like debris after a break-in. Then there's the dark matter dilemma. In most galaxies, the halo isn't just a home for stars, it's where dark matter concentrates, its gravity shaping the entire system. The LMC's near-empty halo forces us to ask, where's its dark matter hiding? Either the galaxy formed with an unusually lopsided dark matter distribution, or something stripped it away, maybe the Milky Way's gravity, siphoning off invisible particles like a thief in the night. The most tantalizing possibility is that we're seeing the aftermath of a cosmic near-miss. Computer simulations show that when two galaxies graze each other close enough to interact but not merge, their halos can be sheared away like cotton candy caught in the wind. If the LMC once had a close call with another galaxy, the encounter might have ripped away both its outer stars and dark matter, leaving behind the pared-down version we see today. What makes this ghostly halo so much more than an astronomical oddity is what it reveals about galaxy evolution on the smallest scales. The LMC isn't just a shrunken Milky Way, it's proof that dwarf galaxies live by different rules, their histories written in the gaps as much as the stars. Every underpopulated parsec is a silent witness to forces we're only beginning to understand, reminding us that sometimes the emptiest places hold the loudest secrets. Most star clusters drift through galaxies like cosmic islands, independent, solitary, but in the Large Magellanic Cloud, there's a pair that defies the norm. NGC 1850 isn't just one cluster, it's two, locked in a gravitational dance so close they share a common halo of stars, orbiting each other like celestial waltzers in a hall of mirrors. This double cluster is a cosmic rarity, one of only a handful known to exist, and its very presence in the LMC raises tantalizing questions about how such delicate partnerships survive in a galaxy known for its turbulence. What makes this duo so extraordinary is their contrast. The primary cluster is a young, blazing metropolis of massive stars, their blue-white light ionizing the surrounding gas into glowing nebulae. Just 13 light-years away, practically next door in astronomical terms, orbits its smaller, denser companion, a compact knot of stars that somehow avoided being torn apart by the larger cluster's gravity. Most binary clusters we've found in other galaxies are either widely separated or in the process of merging, but these two have maintained their delicate balance for an estimated 50 million years. That longevity suggests they were born together, twin siblings emerging from the same primordial gas cloud, rather than capturing each other later in life. Their survival is a puzzle. The LMC is a gravitational battlefield where tidal forces from the Milky Way and nearby dwarf galaxies constantly stretch and distort stellar structures. For two clusters to remain gravitationally bound here is like balancing a pair of marbles on a trampoline while someone jumps. It shouldn't last. Yet NGC 1850 endures, hinting that the gas cloud from which it formed was unusually stable, or that the cluster's orbits are finely tuned to resist disruption. Some simulations suggest their mutual gravity creates a protective bubble, shielding them from external disturbances like a pair of dancers spinning fast enough to ignore the wind. Then there's the mystery of their stars. The larger cluster's stellar population is textbook, massive, short-lived stars dominating its core, but the smaller cluster defies expectations. Spectroscopy reveals an overabundance of blue straggler stars that appear younger and hotter than their surroundings. These are likely stellar zombies, the products of cosmic cannibalism where stars collide or strip material from neighbors, rejuvenating themselves in the process. The tight quarters of the smaller cluster would make such violent encounters inevitable, turning it into a stellar thunderdome where only the strongest survive. But the real revelation lies in what this pair tells us about the LMC's wild youth. Binary clusters are thought to form in the aftermath of galactic collisions or during periods of intense star formation where gas clouds fragment into multiple dense knots. The fact that NGC 1850 exists suggests the LMC once experienced a cataclysmic burst of creation, one violent enough to forge these gravitational twins. It's a living fossil of that era, a snapshot of chaos frozen in time, and their fate, eventually, the larger cluster's stellar winds and radiation will erode its smaller companion, stripping away stars until only the core remain. But for now, they spin on a rare cosmic partnership, a fleeting dance of gravity and light, and a reminder that even in the turbulence of the LMC, beauty can emerge from the chaos. Amid the bustling star fields of the Large Magellanic Cloud, where most structures announce themselves with bright clusters and glowing nebulae, astronomers have spotted something that almost wasn't there at all, a wispy, faint smudge so diffuse it barely registers against the cosmic backdrop. This ghostly object, tentatively named Object Name, doesn't look like much at first glance. It lacks the dense core of a typical galaxy, the sparkle of young star clusters, even the ruddy glow of aging stellar populations. Instead, it's a handful of stars scattered across an improbably vast volume of space, as if someone took a normal galaxy and stretched it thin like cosmic taffy. Yet this unassuming blur might be one of the most revolutionary discoveries in the LMC, a potential ultra-diffuse galaxy, a category so puzzling it's forcing us to redefine what a galaxy even is. What makes this object so baffling isn't just its faintness, it's the sheer mismatch between its size and its substance. Spanning thousands of light years, it dwarfs many conventional dwarf galaxies, yet contains fewer stars than some globular clusters. If it were a city, it would be a metropolis with the population of a small town, endless streets lined with just a handful of houses. Normally, structures this sparse shouldn't hold together at all. Their stars should drift apart, unbound by gravity. Yet here it is, stubbornly maintaining its shape against all expectations. The leading theory suggests this might be a galaxy that lost almost everything but its pride. Born in the early universe, it could have been a normal dwarf galaxy until gravitational encounters with the LMC or Milky Way stripped away its gas and dark matter, leaving behind a skeleton of stars. Alternatively, it might have formed in a uniquely quiet pocket of space where sluggish gas clouds never collapsed into denser structures. Either way, its existence challenges the traditional galactic playbook where size and star count typically go hand in hand. But the real puzzle is how it survived. Without the gravitational anchor of dark matter, thought to be scant in ultra-diffuse galaxies, its stars should have scattered like marbles on a tilted table. Some researchers speculate its stars might be orbiting an invisible reservoir of dark matter after all, one that's distributed so evenly it doesn't clump into a detectable core. Others propose the galaxy is a temporary illusion, a chance alignment of unrelated stars that will disperse over time. Then there's the LMC connection. If this object is indeed a satellite of the LMC, it raises questions about how many other ultra-diffuse galaxies might lurk unseen around larger galaxies, overlooked because they're too faint. Their presence could rewrite galactic hierarchies, proving that size alone doesn't dictate cosmic importance. What makes this faint smudge so captivating isn't just its defiance of categories, it's the possibility that we've been missing an entire population of similar ghosts. If ultra-diffuse galaxies are more common than we thought, they might represent a missing link in galaxy evolution, the quiet majority overshadowed by their brighter cousins. For now, this ethereal candidate lingers at the edge of detection, a whisper in the cosmic dark, and that's exactly what makes it unforgettable. Galaxies usually wear their magnetic fields like invisible cloaks woven neatly along their spiral arms, but the Large Magellanic Cloud has tossed that pattern out the window. Its magnetic field isn't just misaligned, it's downright rebellious, looping and twisting in directions that seem to ignore the galaxy's structure entirely. From a distance, the field resembles a tangled spiderweb, its threads stretching across the spiral arms rather than following them. an anomaly so striking it's forcing astronomers to reconsider how magnetic fields are born and what might be warping them in this cosmic oddball. The first clue to this mystery came from polarized starlight. As light passes through magnetized regions of space, its waves align with the field's orientation like compass needles. When telescopes mapped this polarization across the LMC, they expected to see orderly lines tracing the galaxy's graceful arcs. Instead, they found chaos field lines kinked, fractured, and even running perpendicular to the arms. It's as if someone took a perfectly folded magnetic map and crumpled it into a ball. One explanation points to the galaxy's turbulent history. Magnetic fields in spiral galaxies are thought to grow slowly over time, amplified by the steady churn of rotating gas clouds, a process called the dynamo effect. But the LMC's chaotic structure, shaped by collisions and tidal forces, might have disrupted this natural growth. Imagine trying to knit a sweater while riding a roller coaster. The result would be as messy as the LMC's magnetic web. Computer simulations suggest that encounters with the Small Magellanic Cloud or Milky Way could have yanked the field out of alignment, leaving it frozen in a state of gravitational whiplash. Then there's the dark matter wildcard. Most models assume magnetic fields are shaped by visible matter, stars and gas, but the LMC's lopsided dark matter distribution might be warping space in ways that twist the field unpredictably. If dark matter clumps generate subtle gravitational tides, they could be tugging at the field like invisible fingers, reshaping it into its current, scrambled configuration. But the most tantalizing theory involves the field's primordial origins. Some researchers argue the LMC's magnetism isn't a product of its recent turmoil at all. It's a relic from the early universe, a fossilized imprint from a time when magnetic fields were woven into the fabric of space itself. If true, this tangled web might be a rare glimpse into conditions billions of years ago, preserved in the LMC's isolation like a cosmic time capsule. What makes this magnetic puzzle more than just academic is its ripple effect. Magnetic fields shape how galaxies form stars, guiding the collapse of gas clouds and the flow of cosmic rays. A disordered field like the LMC's could explain why its star formation is so erratic, with nurseries flaring up in seemingly random pockets. It might even influence the galaxy's eventual fate, as misaligned fields resist the orderly collapse needed to fuel future stellar generations. For now, the LMC's magnetism remains one of its most cryptic features, a reminder that even the forces we can't see play by their own rules, twisting the cosmos into shapes we're only beginning to decode. The faintest clues sometimes tell the most dramatic stories, and wrapped around the Large Magellanic Cloud like a tattered celestial banner, there's a clue that could rewrite this galaxy's entire history. Astronomers call it a stellar stream, an ethereal chain of stars so tenuous it barely registers against the blackness of space. But look closer, and this cosmic ribbon reveals a violent past, the shredded remains of a dwarf galaxy torn apart by the LMC's gravity, its stars now stretched into a glittering arc orbiting their destroyer. If confirmed, this ghostly structure would be the smoking gun of galactic cannibalism, proof that the LMC isn't just a passive neighbor, it's a predator. What makes stellar streams so revelatory is their fragility. Unlike globular clusters or dwarf galaxies bound by gravity, these filaments are cosmic crime scenes, their stars barely clinging together as they trace the path of their original orbit. The mere existence of one around the LMC suggests a recent feast, astronomically speaking, at least. Based on the stream's tentative length and dispersion, the devoured galaxy likely met its end within the last 1 or 2 billion years, a blink of an eye compared to the universe's 13.8 billion-year lifespan. But here's where the plot thickens: the stream's chemistry. Initial spectroscopic studies of its stars reveal an abundance of elements like barium and europium heavy metals typically forged in the hearts of ancient low-mass stars. That fingerprint suggests the victim wasn't some fledgling collection of stars, but a mature dwarf galaxy with a long history of stellar generations, possibly even older than the LMC itself. It's as if a lion swallowed a wolf and inherited its teeth. The stream's trajectory adds another layer of intrigue. Unlike the orderly orbits of the LMC's native stars, this structure loops around the galaxy at a steep angle, almost perpendicular to its disk. Such an extreme path implies the dwarf galaxy didn't spiral gently inward. It plunged, likely after being yanked off course by a gravitational tug of war between the LMC and the Milky Way. Simulations of this three-body chaos show how such encounters can fling smaller galaxies onto suicidal orbits, their doom sealed by forces beyond their control. Then there's the dark matter dilemma. If the devoured dwarf was anything like today's surviving counterparts, it should have been anchored by a hefty dark matter halo. When the LMC ripped it apart, that invisible matter wouldn't have simply vanished. It would have mixed into the LMC's own halo, potentially explaining some of the anomalies in its gravitational field. The stream stars might just be the visible tip of a vast, unseen merger, one that pumped the LMC full of dark matter we can't directly detect. But the most tantalizing question isn't about the past, it's about the future. Stellar streams don't last forever. Over time, galactic tides pull them apart, their stars scattering into the halo like sugar dissolving in water. The fact that this one remains coherent suggests the LMC's feeding frenzy might be ongoing. Could other dwarf galaxies be circling, destined for the same fate? Are we witnessing the LMC in the act of growing larger, one meal at a time? For astronomers, this potential stream is more than a fossil, it's a time machine. By reverse engineering its star's motions, they could reconstruct the LMC's gravitational field in 3 dimensions, mapping not just where it's been, but where it's headed. And in a universe where galaxies rise and fall by consumption, that knowledge might just reveal the ultimate fate of our own cosmic neighborhood. In the stellar retirement homes of the Large Magellanic Cloud, where ancient stars should glow with the gentle red hue of old age, astronomers keep finding rebellious outlier stars that dress too young for their time. These celestial imposters, called blue stragglers, burn hot and blue like stellar teenagers despite being billions of years old. They're the cosmic equivalent of finding a pensioner with the muscle tone of an Olympian. And the LMC isn't just hosting a few of these oddballs, it's overrun with them, packing nearly twice as many as predicted. Their very existence flips the script on stellar evolution, hinting at a galaxy where stars don't age quietly, but steal extra fuel or swap identities in dramatic cosmic makeovers. The mystery begins with their color. In any star cluster, astronomers expect to see a clear hierarchy. Massive blue stars die young, leaving behind smaller, cooler red stars as the dominant population over time. Blue stragglers break this rule by lingering in clusters long after their peers have faded, shining with the intensity of stars half their age. The LMC's surplus suggests something unusual is happening in its stellar nurseries, a phenomenon far more common here than in our Milky Way. The leading theory for their origin reads like a cosmic crime drama. Some blue stragglers might be thieves, binary systems where one star siphons hydrogen from its companion, rejuvenating itself with stolen fuel. Others could be the products of violent collisions where 2 aging stars slam together and merge, their combined mass reigniting nuclear fusion with newfound intensity. Picture 2 dying campfires shoved together suddenly. They flare up brighter than ever, but the LMC's dense, chaotic environment adds another twist. Its star clusters are packed so tightly that stellar encounters happen frequently, turning them into perfect laboratories for both theft and collision scenarios. In one well-studied cluster, researchers found blue stragglers concentrated at the core, exactly where gravitational interactions are most violent. It's as if the galaxy's crowded dance floors keep spitting out these oddities, their formation encouraged by the constant jostling of stellar neighbors. Then there's the chemical evidence. Many of the LMC's blue stragglers show abnormal abundances of elements like carbon and nitrogen in their atmospheres, a smoking gun of internal material dredged up during mergers or mass transfer. Some even pulse rhythmically, their surfaces heaving like overfilled water balloons, a sign of structural instability from recent stellar trauma. These aren't just stars pretending to be young, they're stars fundamentally altered by extreme events. Their impact goes beyond mere curiosity. Blue stragglers can skew our measurements of a galaxy's age and distance, as their unexpected brightness throws off standard stellar benchmarks. More profoundly, they're proof that stars don't always follow solitary paths sometimes. Their fates intertwine in ways that rewrite their lifespans. In the LMC, where stellar interactions are amplified by the galaxy's unique chemistry and density, these outliers aren't exceptions, they're inevitabilities. And so the blue stragglers continue to burn, defiant against time, each one a testament to the galaxy's turbulent social dynamics. Whether thieves, merger survivors, or products of celestial chaos, they remind us that in the cosmos, aging isn't just a process, it's a negotiation. When a star dies in a supernova explosion, it's supposed to leave behind a calling card, a glowing, expanding shell of debris that shines brightly in radio waves and X-rays for thousands of years. But the Large Magellanic Cloud is home to a group of cosmic ghosts, supernova remnants that have gone rogue, fading into near invisibility when they should still be blazing across the electromagnetic spectrum. These invisible remnants aren't just hiding, they're breaking the rules of stellar death, forcing astronomers to question whether we've misunderstood how these explosions interact with their surroundings. The mystery starts with what we don't see. In our own Milky Way, supernova remnants like the Crab Nebula or Cassiopeia announce their presence with fierce X-ray emissions and radiostatic, the result of shockwaves accelerating particles to near light speeds. But in the LMC, surveys have uncovered multiple remnants that glow faintly in optical light, telltale filaments of ionized gas, while emitting almost no radio or X-ray signals. It's like finding the charred aftermath of a fireworks display without any evidence of the explosion itself. What could possibly silence a supernova's aftermath so completely? One clue lies in the environment. The LMC's interstellar medium, the sparse gas between its stars, is far less dense than the Milky Way's. When a supernova blast wave encounters thin gas, it expands more rapidly, dissipating energy before it can heat particles enough to produce strong X-rays or radio waves. Imagine shouting into a thick fog the sound carries, but shout into an empty field, and your voice vanishes almost instantly. These remnants might simply be fading into the LMC's cosmic quiet. Then there's the magnetic field factor. Invisible remnants often coincide with regions where the LMC's tangled magnetism is exceptionally weak. Magnetic fields are crucial for revving up electrons to radio-emitting energies. Without them, the shockwave might sail through space like a ship without a sail, leaving no detectable wake. Some of these remnants could even be expanding into pre-existing bubbles blown by the progenitor star's stellar winds, a cosmic vacuum where there's simply nothing to light up. But the most tantalizing explanation is that we're witnessing a rare breed of supernova, one that leaves behind far less debris than usual. Most remnants we study come from core collapse supernovas, where massive stars implode and rebound in a fiery outburst. But if some of the LMC stars died in electron capture, supernovas a rarer, milder explosion triggered by unstable neon atoms in a star's core. They might produce weaker shocks and lighter remnants. These cosmic whispers could be the first clear evidence of such explosions occurring en masse outside our galaxy. The implications stretch beyond the LMC. If invisible remnants are common here, they might lurk undetected in other galaxies too, silently skewing our tallies of stellar deaths. Every missing remnant throws off calculations of star formation rates, metal enrichment, even the galaxy's energy budget. Worse yet, some of these ghosts might overlap with the LMC's missing red supergiant stars that vanished without the supernova fanfare we expected. Could they be connected? For now, these faint echoes linger at the edge of detection, their very invisibility a beacon pointing to gaps in our understanding. They're reminders that even the universe's most violent events can leave behind the quietest traces, if we know where to look. Deep in the heart of the Large Magellanic Cloud, hidden among its chaotic stellar nurseries and spinning stellar corpses, there's a cosmic radio station broadcasting messages we've only just begun to decode. Fast radio bursts those fleeting, millisecond-long blasts of radio energy that flicker across the universe have mostly been traced to distant galaxies billions of light-years away. But the LMC hosts one of the closest known FRBs ever detected, a repeating burst that crackles to life just over 160,000 light-years from Earth. What makes this discovery so electrifying isn't just its proximity. It's the unnerving possibility that the LMC's turbulent environment might be actively cooking up these enigmatic signals. Most FRBs are cosmic loners erupting once and vanishing without a trace, but the LMC's burst, dubbed FRB 2021-117, is a repeater, firing off multiple pulses since its discovery. That behavior immediately narrowed the list of suspects. Repeating FRBs are thought to originate from magnetars, the universe's most magnetic stellar corpses. These neutron stars pack the mass of a sun into a city-sized sphere, wrapped in magnetic fields so intense they could strip the data from a credit card halfway across the Milky Way. And the LMC just so happens to be crawling with them. This galaxy's chaotic star-forming history has left behind an unusually high concentration of these magnetic monsters. When massive stars die in supernova explosions, their cores can collapse into neutron stars, and if conditions are just right, those remnants spin up into magnetars, their magnetic fields amplified to unimaginable levels. The LMC's history of violent stellar births and deaths makes it the perfect magnetar factory, churning out these extreme objects at a rate that outpaces even our own galaxy. But here's where the mystery deepens. Not every magnetar produces FRBs. In fact, out of the dozens we've catalogued in the Milky Way, only one SGR 1935 plus 2154 has ever been caught emitting an FRB-like signal. So why would the LMC's magnetars be so much more prolific? The answer might lie in the galaxy's youth. With its lower metal content and frenetic star formation, the LMC's magnetars could be born spinning faster and with more twisted magnetic fields than their Milky Way counterparts, priming them to unleash these explosive radio bursts. Then there's the environment itself. FRB 2021-1117 isn't floating in isolation. It's embedded in a dense star-forming region, surrounded by hot gas and turbulent magnetic fields. Some theorists propose that these external factors could be acting like a cosmic amplifier, squeezing the magnetar's magnetic field lines until they snap, releasing energy in the form of FRBs. It's akin to the difference between a lightning bolt in open air versus one channeled through a narrow metal rod. The surrounding medium shapes the explosion. But the most tantalizing clue comes from timing. The LMC's FRB erupted around the same epoch as a detected uptick in gamma-ray activity from the same region. If confirmed as linked, it would be the smoking gun connecting FRBs to magnetar flares, an idea long theorized but rarely proven. Imagine a neutron star's crust cracking under magnetic strain, unleashing a gamma-ray burst, and then, like an aftershock, the twisted field lines rebounding to produce an FRB. The LMC's unique vantage point gives us a front-row seat to test this scenario, with details too faint to spot in distant galaxies. Of course, alternative explanations still linger. Some researchers speculate that FRBs could arise from collisions between neutron stars and asteroids, or even exotic dark matter interactions. The LMC's abundance of dense stellar remnants and turbulent gas clouds provides fertile ground for all sorts of high-energy oddities. But with every new burst detected from FRB 2021-1117, each one a little different from the last, the magnetar case strengthens. What makes this discovery more than just a local curiosity is what it reveals about FRBs across the cosmos. If the LMC's unique environment really does encourage these bursts, it suggests that galaxies with similar properties, young, metal-poor, and bursting with star formation, might be FRB hotspots in the early universe. That could explain why we detect so many from billions of light-years away. We might be seeing echoes of a time when galaxies like the LMC were the norm, not the exception. For now, every pulse from this nearby FRB is a piece of the puzzle, a whisper from a magnetar caught in the act, and in a galaxy already overflowing with cosmic anomalies, it's just another reminder that the LMC never follows the script. The Large Magellanic Cloud shouldn't be this dusty. That's the glaring paradox baffling astronomers. A galaxy with just 20% of the Milky Way's heavy elements somehow churns out vast clouds of cosmic dust, enough to shroud entire stellar nurseries in veils of silicate and carbon grains. This isn't just a small discrepancy, it's a full-blown rebellion against our understanding of how dust forms in the universe. In most galaxies, dust production relies on metals, elements heavier than hydrogen and helium as building blocks. Yet here's the LMC, a cosmic underdog with barely a fifth of our galaxy's metal content, pumping out dust like an industrial factory. How does it defy the rules so spectacularly? The mystery begins with dust's origins. In metal-rich galaxies like ours, dust grains condense in the cooling winds of aging stars, where abundant silicon, carbon, and iron atoms clump together into microscopic particles. These grains then drift into interstellar space, seeding future generations of stars and planets. The process is so efficient that astronomers once assumed low-metal galaxies like the LMC would be dust deserts. Yet when telescopes like ALMA and Spitzer peered into its heart, they found sprawling dust lanes, glittering nebulas, and even protoplanetary disks around young stars, all hallmarks of a surprisingly dusty environment. One clue lies in the LMC's star-forming frenzy. While the Milky Way forms stars at a leisurely pace, the LMC experiences violent bursts of creation, with supernovas and massive stellar winds shredding through gas clouds at unprecedented rates. These explosions don't just forge heavy elements, they create turbulent conditions where atoms collide and stick together far more efficiently than in common galaxies. Imagine a blacksmith's workshop versus a quiet lab. The chaos of the forge might produce more particles simply because everything's moving faster and smashing harder. Then there's the carbon factor. Dust in the LMC skews heavily toward carbon-based grains, unlike the silicate-dominated dust of metal-rich galaxies. Carbon, it turns out, can form chains and rings even in low-metal environments, especially around carbon-rich Wolf-Rayet stars and aging red giants. These stars act like cosmic 3D printers, spewing sooty carbon compounds into space where they coalesce into dust. The LMC's unique stellar population, packed with short-lived massive stars, might be leaning into this alternative dust pathway, exploiting carbon's versatility to compensate for the lack of heavier elements. But the real twist comes from supernova surprises. Recent studies of the LMC's supernova remnants reveal something startling. These explosions might be better at making dust in metal-poor conditions. When a star dies in a metal-rich galaxy, its expanding shockwave can destroy existing dust grains faster than new ones form. But in the LMC's sparse environment, the same shocks have less material to plow through, allowing freshly minted grains to survive and accumulate. It's like trying to build a sandcastle in a hurricane versus a breeze sometimes. Less interference means more construction. What makes this dust paradox so much more than an academic curiosity is its cosmic implications. Dust isn't just space pollution, it's the raw material for planets and the catalyst for molecule formation, shielding fragile compounds from destructive radiation. If the LMC can produce dust against all odds, it suggests the early universe, even more metal-poor than today's LMC, might have been dustier than we thought. That revelation could reshape our models of how quickly planets and life's ingredients emerged after the Big Bang. For now, the LMC's dust remains a beautiful contradiction, a reminder that the universe often finds loopholes in the rules we write for it. Every speck of its unexpected dust is a clue, not just to this galaxy's secrets, but to the untold stories of galaxies far beyond. Deep in the crowded star fields of the Large Magellanic Cloud, something massive is hiding in plain sight, a gravitational phantom so elusive, astronomers have spent decades chasing its shadow. Among the galaxy's dense clusters and chaotic nebulae, there's mounting evidence for an intermediate mass black hole, a cosmic missing link tipping the scales at hundreds or even thousands of solar masses. Unlike the stellar mass black holes formed from collapsing stars or the supermassive giants anchoring galaxy centers, these middleweights have long resisted detection. But the LMC might finally be giving up its secret, offering clues that could solve one of astrophysics' most persistent puzzles. The first whispers of this hidden predator came from an unlikely source, the runaway stars. Hypervelocity stars streaking through the LMC at impossible speeds, like the one clocked at over 1,500 kilometers per second, point to gravitational encounters too violent for ordinary stellar remnants to explain. Slingshotting a star to such extremes requires a black hole far heavier than the typical collapsed star, something in the intermediate range. Then there's the curious case of a dense star cluster called R136, where stars orbit an invisible point with frantic urgency, their motions betraying the pull of an unseen object roughly 3,000 times the mass of our Sun. But why is this black hole so hard to pin down? Intermediate mass black holes occupy an awkward niche, too small to dominate their surroundings like supermassive black holes, yet too large to form through standard stellar collapse. They're the cosmic equivalent of a Yeti, theoretical footprints everywhere but no definitive sighting. Some models suggest they could be primordial, born in the chaos of the early universe before galaxies took shape. Others argue they're the grown-up versions of stellar mass black holes, bulking up over eons by swallowing stars and gas or merging with siblings. The LMC's turbulent history makes it a perfect incubator for either scenario, a place where gravitational chaos could have forged a black hole stuck between categories. The hunt now hinges on two fronts. First, astronomers are scouring the LMC's dense clusters for X-ray flickers, the telltale glow of gas heated to millions of degrees as it spirals into a black hole's maw. So far, the signals have been frustratingly faint, suggesting the black hole might be starved of fuel, lurking quietly in the dark. Second, they're tracking the precise orbits of stars near suspected locations, looking for the subtle wobbles that would betray an invisible companion. It's like trying to spot a hawk by watching the panic in a flock of sparrows. What makes this search so crucial isn't just ticking a box on the black hole family tree. Intermediate mass black holes could be the seeds from which supermassive black holes grow, the missing link in galactic evolution. If the LMC hosts one, it challenges our assumptions about how dwarf galaxies form and whether they too might cradle these gravitational anomalies in their cores. Every unexplained stellar trajectory, every flicker of high-energy light, brings us closer to confirming a presence that's been hiding just next door, a reminder that sometimes the most profound discoveries aren't in the distant cosmos, but in the details we've overlooked closer to home. The Large Magellanic Cloud isn't just our galactic neighbor, it's a ticking time bomb on a collision course with the Milky Way, and its bizarre behavior could rewrite our galaxy's future. Current simulations paint a dramatic scene. In about 2.5 billion years, the LMC's orbit will decay, sending it spiraling into our galaxy's embrace. This won't be a gentle merger like the one awaiting Andromeda and the Milky Way in the distant future. The LMC's peculiar traits, its missing dark matter, rogue stars, and chaotic structure, mean this collision won't follow the usual galactic playbook. Instead, it could unleash a chain reaction of cosmic chaos, reshaping everything from our galaxy's spiral arms to its central black hole. What makes this impending merger so volatile is the LMC's staggering speed. Unlike most satellite galaxies, which orbit passively until gravity pulls them in, the LMC is barreling toward us at nearly 300 kilometers per second. When it finally plunges into the Milky Way's disk, the impact will send shockwaves through both galaxies, triggering bursts of star formation so intense they'll outshine entire constellations. But the real wild card is the LMC's gas content. Despite its small size, this galaxy is a floating reservoir of pristine hydrogen fuel that hasn't been contaminated by generations of supernovas. As it collides with the Milky Way's denser gas clouds, that untouched material could ignite a firestorm of new stars, flooding our galaxy with young, blue clusters in a celestial baby boom. Then there's the dark matter dilemma. The LMC's unusually low dark matter content means its gravitational footprint won't match predictions. Normally, galaxies like it act as anchors, stabilizing their hosts by distributing dark matter evenly. But the LMC's lopsided halo could warp the Milky Way's own dark matter distribution, potentially flinging stars out of their orbits or even disrupting the delicate balance that keeps our spiral structure intact. Some models suggest the collision might puff up the Milky Way's disk, transforming it from a sleek spiral into a more disorganized, thick disk galaxy over billions of years. But the most explosive variable lies at the heart of the LMC, its possible intermediate mass black hole. If one exists and evidence is mounting, it could be flung toward the Milky Way's center during the merger, eventually sinking to our galaxy's core and merging with Sagittarius, a star. The resulting gravitational waves would ripple across the universe, and the energy released could light up our galactic center like a cosmic flare. Meanwhile, the LMC's runaway stars and rogue clusters, already unbound by its weak gravity, might scatter across the Milky Way like shrapnel, some ejected into intergalactic space while others join our galaxy's halo. This collision isn't just a future spectacle, it's already begun. The LMC's current trajectory is dragging the small Magellanic Cloud along with it, stretching both galaxies into a stream of gas and stars known as the Magellanic Stream. By the time the final merger occurs, this ribbon of material will have wrapped around the Milky Way like a cosmic lasso, funneling fresh gas into our galaxy long before the main event. For astronomers, that makes the LMC a preview of the universe's relentless dynamism, a reminder that even the quietest corners of space are never truly still. The Milky Way may seem eternal from our fleeting human perspective, but its fate, and ours, is already entwined with this turbulent dwarf next door. From runaway stars defying gravity to ghostly gamma-ray bubbles towering over the galaxy, the Large Magellanic Cloud is a cosmic hall of mirrors, each reflection shattering another assumption we held about how the universe works. Take the Tarantula Nebula, a stellar factory operating at impossible brightness, or N44's superbubble, a void carved by forces we can't fully explain. The LMC's rogue black holes, missing red supergiants, and carbon stars bursting with unexpected abundance all whisper the same truth: astrophysics textbooks are incomplete. Even its magnetic field swirls in rebellion, tangled like a snarled cassette tape, while its dark globular clusters hide masses we can't see, possibly swarms of black holes or dark matter clumps laughing at our models. Then there are the X-ray binaries erupting like clockwork, the stellar vampirism of blue stragglers, and the planetary nebulae that vanished without a trace. These aren't isolated oddities, they're interconnected clues. The LMC's warped disk reveals the violence of its past collisions, while its tidal dwarfs prove galaxies can form from galactic wreckage. And lurking beneath it all, the tantalizing possibility of an intermediate mass black hole, a missing link in cosmic evolution pulling strings we're only beginning to sense. This galaxy forces us to ask uncomfortable questions. Why do stars in metal-poor environments die so quietly? How do magnetic fields fossilize chaos? Every phenomenon here, from the faintest stellar stream to the brightest recurrent nova, isn't just a puzzle, it's a key. Keys to understanding dark matter's quirks, the birth of elements, even how galaxies like ours might evolve when the LMC collides with the Milky Way in billions of years. So as we close this journey, consider this. If a single dwarf galaxy next door can upend so many expectations, what wonders wait in the uncharted depths beyond? The universe isn't just stranger than we imagine. It's stranger than we can imagine. Keep looking up, stay curious, because the next cosmic revelation might be hiding in plain sight, just like these 30 mysteries once were.